Okay, the final video in the pricing and revenue management section is about overbooking when you have excessive cancellations. It's a very common thing, especially with hotel rooms and airline tickets and all those sorts of perishable inventories. And so here the basic trade-off is between wasted capacity and shortage of capacity, right? So this is very similar to what we looked at in the news vendor model with overstocking and understocking. So think of it this way. So if inventory is the number of excessive rooms that you have, so overstocking and understocking work very similarly. So CW essentially is the cost of wasted capacity. How much? What is the? How much does it cost you if you have too much capacity left over? Right? You could have done something with it, but you were not. So that's a lost revenue. And CS is the cost of shortage. And then we calculate the ratio just like we did before, and then we calculate the optimal and we calculate the optimal overbooking level based upon that. And now, when calculating the optimal overbooking level, let me just switch over to the textbook for a second. In calculating the optimal overbooking level, there are two ways in which demand can be known. So if the demand distribution is known, let's say, so this is the formula for calculating the overbooking level. If demand distribution is, say, we look at normally distributed demand distributions, but if we know the mean and standard deviation of this normally distributed demand of this normal distribution, it's a very straightforward calculation, very simple, just like we did with the news vendor model. We can calculate the optimal. So this is the I'm sorry, this is not the optimal overbooking level. This is just the critical ratio, and then we can calculate the optimal overbooking level using the inverse of the normal distribution. But in a lot of these situations, you only know the normal distribution as a function of the overbooking level and the mean and standard deviations. Instead of knowing them directly, you know them as a percentage of something or something like that, right? So let's look at a concrete example, and then we'll talk about what we're talking about here. So let's consider an apparel supplier that is taking orders with a Christmas motif. The production capacity available for the supplier is 5,000 dresses, and they have a margin of $10 for every dress they. So basically, that is the price they're selling minus the cost. So that's how much money they are making per dress, right? The supplier is currently taking orders from retailers and must decide on how many orders to commit to at this time. At the time of the delivery, if the supplier has orders that exceed capacity, right, it must arrange for backup capacity, and which results in a loss of $5 per dress. So basically, you're saying that if you if you if you commit to making too many dresses, and suddenly you need, say, 10 more dresses or something, you might have to subcontract it out to somebody else or buy it on the open market from somewhere else, or whatever that happens. You expect a $5 loss per dress if you do that, either with the subcontracting or something else. Now, in all of this, the uncertainty that we are facing here mainly is we don't know how many cancellations we are going to have. So this overbooking is based on the distribution of those cancellations. So retailers have been known to cancel their orders once they get better visibility of expected demand. So how many orders should the supplier accept if cancellations are normally distributed with a mean of 800 and a standard deviation of 400? So if we know the normal distribution in a very simple way, just like this, with a mean of 800, standard deviation of 400, the calculation is very straightforward. But if the distribution is given to you this way, how many orders should the supplier accept if cancellations are normally distributed with a mean of 15% of the orders accepted, and the coefficient of variation is zero point 0.5? So you're saying that about 15% of the orders are going to be cancelled. It's a very common way of figuring out how many cancellations you have, what percentage of the orders are going to get cancelled. And coefficient of variation, this is not standard deviation, but coefficient of variation is just the ratio of mean to the standard deviation to the mean. It's standard deviation divided by mean. That's the coefficient of variation. And in some cases, it might be easier to find the coefficient of variation rather than the standard deviation itself, right? So in both of these cases, we'll calculate how many orders should the supplier be accepting, even though they have they have a production capacity of 5,000 only. So they should obviously be overcommitting, but by how much should they be overcommitting by, right? So let's do those calculations, right? So let's begin with this. So the cost of wasted capacity. So let me just scroll it up like that. So cost of wasted capacity, so that's CW is $10, and the cost of capacity shortage is $5. And so the critical ratio, so I'm calling it as star here. Critical ratio is CW divided by CW plus CS. So this is exactly like CU divided by CU plus CO that we had in the news vendor case, right? So 66.67, so 2/3 is the is the oops, yeah, 2/3 is the capacity, is the probability that we have here. With that, now if the mean and standard deviation are known in a straightforward way, so if cancellations are normally distributed with a mean of 800, standard deviation of 400, so mean standard deviation. So in this case, if you know the mean and standard deviation, so let's say that mean is 800 as it's given there, and standard deviation is 400. Then the overbooking is very straightforward to calculate. This is the same way you calculate safety stock. So overbooking is essentially safety stock is norm.inv with a probability of 66.67, 2/3, and with a mean of 800, standard deviation of 400, right? So 972. Let's round that. Just going to use the round function around it with 0 decimals. Right, 972. And so the total accepted orders. So how many orders should they accept? Well, they have a capacity of 5,000, and so they should overbook by 972. So it'll be 5,000 plus 972, right? 5,972. That's how many orders they should accept, right? Now instead, excuse me. So the same data, just going to copy that over. Right. Now mean and standard deviation are given to us differently here, and so that's something to keep in mind. We know that mean is, so yeah, okay. So we know that mean is 15% of the booking level. So whatever booking level you have, 15% of that booking level is going to be the mean. So it's going to be 15%. 15% of the booking level. So let me write the same formulas here just for the time being. It's going to be bad. So mean is going to be 15% of whatever the booking level is. Now booking level won't be exactly 5,000, it'll be different from that, obviously. Standard deviation is, so we have a coefficient of variation of 0.5, which means it'll be 0.5 times whatever the value of the mean is. So standard deviation divided by mean is 0.5. So standard deviation is mean times 0.5, right? That's going to be the case, and then that's the overbooking. That's the overbooking value. So let me insert row here. So, like I said, it's way more complicated in this case because of the way the formula is written up. So, in this case, I'm just going to say it's just repeating the same number. So, it'll be 5,000 plus that, right? So, even in this case, it's going to be 5,000 plus that. Okay, now again here I'm going to write the same formula right here. So normal inverse of the normal distribution with the mean of this and standard deviation of that, right? Now the only difference is if I type in a 300 here, for example, so this number of overbooked rooms, this formula for the number of overbooking rooms that we have right now is assuming that the number of orders we accept is 5,000, because 15% of 5,000 is 750. But let's say that the number of overbooked rooms is 100 for the sake of argument, right? The number of overbooked room, let's make it 500. If the number of overbooked room is 500, now the mean and the standard deviation values themselves have changed. So the overbooking formula is going to give you a different number. So there is no easy way to do this, and we can't even do this with what if, because the value that we're trying to figure out is different. We could potentially do this with the solver, but the easy method is, what you need to do is, if you look at the total number of accepted rooms or orders, you're saying 5,000 orders is baseline. You're going to accept 5,000 orders minimum. You're trying to figure out how many more to accept, and that's the number here. So you have to keep adjusting this number so that this number that you have here matches the overbooking formula. In that case, both of these numbers are the same and the mean and standard deviation match and everything is okay. So the way this is set up, right, is this is the number of, so if you look at the case when you have mean and standard deviation values very clearly given to you, then both of these numbers are just equal to each other. That's why I just said that this should be equal to that. There is no question here. But because here for us the mean and standard deviation itself depend upon the number of overbooked rooms. So if you go back to the formula, you'll notice that the mean and standard deviation itself depend upon the number of overbooked rooms, because you're saying 15% of the total number of bookings that you have are going to get cancelled. But the total number of bookings also include the number of overbooked dresses. I'm sorry, I keep saying rooms, it's dresses. Right. So you have to keep changing this number so that both of these match each other. So 500 gave us 1,000. So let's do a big change. So if I do 1,000, it is still more. So you'll notice that as this value increases, this value will decrease. Or at least it will go up, but not by. So for example, if this let's say 100, right? So this is 930. If I do 200, this value increased, but this value won't increase at the same level as so this increased by 100, but this increased only by around 30 or 40. If I go up to 500, this also increased. So this increased by 300, but this only increased by maybe 50 units, right? So you keep increasing this till this number matches this number. So if I go up to 1,000 now, you'll notice that this goes up from 1,003 to only 1,094. So we increased this number by 500, but this number only changed by about 91, right? So let's say if I do 1,500, now this number has become more than this number. So our actual value has to be somewhere between 1,000 and 1,500, because if I keep increasing this number, this will go up much faster than this number here. So let's say that I do 1,250. Because I went up from 1,000 to 1,500, I'm going to half it. So if I go down to 1,250, now we are getting closer. This number is still down a little bit. So let's say that, how about 1,200 then? Still not that close. How about 1,150? Oh, we are getting closer, right? 1,125. Ooh, getting much closer. How about 1,120? Getting very close. 1,115. and there's a match, right? These two numbers match, and so the mean and standard deviation and everything matches. So essentially you have to keep changing this number till both of these numbers match. So our number of overbooked dresses, so I keep saying rooms because I have rooms here. Number of overbooked dresses, I'm so sorry about that. Number of overbooked, maybe I'll just say orders, that'll make it easier. The number of overbooked orders is 1115, and the total number of orders that they should accept is 6,150. Right? And that's the idea here. And the reason why this is way more complicated than this value here before, because the mean and standard deviation values are given to you directly, as opposed to here, where the mean and standard deviation itself depend upon the number of overbooked orders. So it's almost like a circular formula, and you have to do everything together at the same time, and it's, yeah, so that's basically that. Okay, so this finishes everything that I wanted to cover in this chapter, and yeah, so I'll see you all later, right? Take care.